Hello everybody and welcome back to the podcast of the InnCoCells project. We are joined by Bart van Drugenbroek, who is from Ilvo. Bart, thank you very much for joining me. I know you're a very busy man. We're in Luxembourg at the moment, having just had our 5th InnCoCells meeting, and now we are still in Luxembourg for a follow-on meeting called Phyto Factories, and Bart is an invited speaker, so he's very kindly found a half hour in his busy schedule. And Bart, to start with, it'd be great if you could tell our listeners a little bit about you're from Ilvo, maybe a little bit about what Ilvo is and what it does, and then we'll maybe talk a bit more about what you do in the InnCoCells project.
Thanks for the invitation.
My pleasure.
So yes, I'm working for Ilvo. Ilvo is a research institute from the Flemish government, and we're actually working for the Ministry of Agriculture, Fisheries and Food. We're a public research institute. And we're collaborating with companies in process and product development. So basically what we do is one-on-one projects with companies to support their innovation in their product and process development. But we also provide some services to the policy domain, policy supportive research, for example, on topics like protein diversification and the development of the bioeconomy in the future. So that's the link with the InnCoCells project. I'm mainly dealing with projects in which we focus on the optimal use of plant biomass, for example. We throw away a lot of byproducts in the agri-food sector, and that's how I got involved in the InnCoCells project. How can we make optimal use of plant cell biomass coming from cell suspension cultures or plants grown in the field, and how to optimally use that, striving for a zero waste approach, making value out of every fraction we generate from the biomass.
Excellent. So would you say this is a major part of Ilvo's work? How many people work there?
We're about 700 people at this moment, and we have 4 big divisions. So we still have a plant science unit, which basically is doing breeding and selection programs on minor crops, which are neglected by the bigger companies. For example, green fodder crops. They are not that popular among the big breeding companies, but they are important in agriculture. For example, to prevent erosion. So that's one of our breeding programs. And during the last century, we also focus on novel protein crops, legume crops. Like, for example, could we grow soybean in Europe? What does it take to make that crop work in Europe? It's adapted to tropical climates, but could it grow in Europe as well? As well as, for example, chickpea, lentils, and other new protein sources that we could use for a plant-based diet. So that's a plant-based science. We have an animal science unit where we look into feed ratio conversion, emissions that contribute to greenhouse gas emission. How can we adapt feed that cattle is producing less emissions, for example, by adapting the feed? That's the main topic. And then I'm belonging to the technology and food science unit, where we focus on processing technology and product development, for example, in agri-food, but also in bioeconomy. And then we have a social science unit, who is more looking at everything that has to do with research in the agri-food sector from a different angle. What about economic sustainability, social sustainability? What about implementation of big greenhouses in a densely populated country like Belgium? Where are there still areas left where we can do that or not? So that's a very nice environment, because we have all these different disciplines together. And if you can tackle a research question with such a big team, that's very nice to do. So I love to work there.
That's good. So you work in the department that deals mostly with processing, and just wanted to put some context into the podcast for the listeners, because I've been actually looking forward to working with Bart for quite some time, because for our regular listeners, they will know that most of our previous interviewees have been working in what we call upstream production. So this is where we generate the biomass for the ingredients that we're trying to make. And others have been working in the analysis of the ingredients. And Bart is the man in the middle. This is the extraction, where we take the biomass and find some way to get the ingredients out. So essentially, I think if I can summarise, Bart is the leader of Work Package 4. We had a couple of episodes ago, we had Jaya, who is the leader of WP3, which is the upscaling of the biomass. So basically, Bart, you will now take whatever biomass is generated and extract the ingredients from it. One thing I'm quite interested in is, I ask a similar question to Jaya. If you have a very small amount of biomass and you apply a certain technique to it, what is the challenge of then saying, okay, here's a kilogram, I'm going to try and get something out of that, and then you scale that up to 50 kilograms or a ton? What is essentially you can't just use the same equipment for longer or just a bigger piece of equipment. It must be something more challenging than that to overcome.
Yeah, that's correct. When we start at lab scale, the conditions are very different. You try to optimize all the factors that might have a negative impact on the quality of your extract. You try to diminish that. But if you scale up to control those conditions, that's more difficult or is done in another way. It is indeed possible for very conventional technology, like producing a hydrophilic extract. You can do that at lab scale, and there is processing technology available to do that at 10 liter, 100 liter, even 1,000 liter scale, perhaps in batch systems. But for industrial implementation, you want to go to continuous systems, where if you have to produce very big volumes of extract, that you also can deal with very big volumes of initial biomass that should be continuously processed. So that's often a big challenge, to turn a batch process into a fully continuous process. But for the project, we aim to do bigger batches and to see what the impact of the upscaling is. Because, for example, the mixing might be just a physical technical problem to mix the biomass and have a good contact with the solvent and the cell and the tissue. So that can be an issue. Control of pH and stuff like that is more standardized, but these upscaling issues, they appear indeed, and it's not always predictable what it will be. So, in fact, you have to do it case by case and see if there are emerging problems. Sometimes there are, sometimes not. So, upscaling really is an important step in the extraction process. And as mentioned yesterday by Kirsi Maria in the meeting, we start from a raw extract and then we test if there's functionality, but probably we can increase the functionality of our extract if we can purify it, if we can remove compounds which do not contribute to the activity. They might even perhaps lower the activity. So if we could remove these, we have a better extract. So that's then the next step. Can we fractionate and isolate the really active ingredients from those that are not active and get to a more purified extract? And then it's depending on the application. And there the link with the companies is really crucial. And that's a nice thing in the consortium, that we can ask these questions right to the experts in the field who are looking for the active ingredients. How pure should they be from both a legislative point of view, from a safety point of view, etc.? How far do we need to go to be successful with a commercial ingredient? And we will learn a lot from that contribution by the companies, which is really nice.
That was actually a very nice summary of the what we might call the value chain that we're covering in the consortium, all the way through from first principles of getting the cells to grow or the plants to grow and optimizing them to produce the ingredients we're looking for, all the way through to the factors to consider in terms of regulatory requirements and commercialization. So that's a pretty broad picture to paint. Maybe I can pin you down to something more specific. In the project, what sort of scale are we talking about that you're dealing with on a day-to-day basis? We're talking about 2 litres, 5 litres, 10 litres, or hundreds or thousands? Or
the ultimate goal is to reach to a scale like, for example, 10 litre, 100 litre scale an hour. For filtration processes, this is the scale we want to go to. Of course, we are not there yet, but we try to bring in some innovations, and especially, for example, in downstream purification, a lot of filtration technology is used. And we encountered an innovative technology where normally ceramic membranes are used. They have specific pore sizes, and due to the nature of the ceramic, some compounds will attach to the surface of the ceramic membranes in the filtration unit. But the problem is that in the end, they will block the pores in the membrane, called membrane fouling, and that will slow down the process. And that's a bottleneck. Now we found out that there's some innovation ongoing in that research field, that you can use organic chemistry to attach organic compounds which act as a ligand to bind specific either components you want to get out of your extract, or you want to attract components that bind to these ligands, organic ligands attached to the ceramic membrane. And the big advantage is that the process runs smoother and longer. There's no membrane fouling, so the speed of the filtration does not go down. And it's organic chemistry, so you can graft other compounds if you want to use the membranes for purifying or removing another organic compound in your filtration unit. So that's a very novel technology, and we hope to test these kind of innovations together with the companies to get breakthroughs in that field as well, because if you have more efficient processes, you will use less energy, less water, and contribute to a more sustainable downstream processing scheme of your product, because downstream processing, as we know, is taking most of the cost. Often in a production process, it can go up to 70-80% of the entire process cost can come from the downstream processing. So processing the biomass is one thing, but getting the extract out is costing a lot more money often than making the initial biomass from which you start for the extraction. So yeah, we hope to collaborate, to bring in some innovations, and then get also the feedback from the companies again to make some progress there.
So putting that more simply, you're talking about taking a membrane which you normally get things sticking to, you don't want to sit, chemically modifying it in some way, and then those things don't stick?
You can work more targeted. The organic compounds attached to the ceramic membrane surface can be chosen in respect to the goals you want to achieve. Do you want to remove a solvent which is still inside? Then you can design a ligand that will attach the ethanol or the DMSO or whatever and keep that out of your filtrate. Or if it's very hard to recover the active ingredient, you can target a ligand on the ceramic surface that will bind very efficiently to the compound you need to purify. So it's quite new. There are some first implementations in industry. There's very little information, but we hope to set up some collaborations and make some progress there.
So you mentioned earlier that the different types of biomass that are coming into the downstream processing part of the project. So you've got plant cell suspension cultures, for instance, you've got hairy roots, you've got whole plants, and you've got, in some cases, some sort of industrial bio-waste, which is organic. Do you have completely different types of challenges when you're handling different types of biomass? Or
there are some common principles, but of course, starting with intact plant biomass, it's very unstable. It's an active physiologic biochemist system where enzymes are still active. So the first thing you want to do is to stop enzymatic activity, avoid breakdown. So what we try to do is to stabilize the biomass in the first step. And often you have to mix or to mill the biomass into finer particles to have improved extraction yields. So when starting from organ cultures like hairy root or from an intact plant, the first step will be to homogenize the plant material and to stabilize it. So in that case, we should avoid oxidation, for example. Flushing with an inert gas like nitrogen during mixing and milling can avoid oxidation, but you can play around with the pH to acidify and avoid that specific enzymes will be active and cause degradation. So that's specific for intact plant biomass and for organs, hairy root cultures, for example. And when dealing with cell suspensions, that's completely different. They are very sensitive to oxidation, to light, etc., because some cell cultures are grown in the dark, for example. So if you would process them in the light, sensitive compounds could break down. So there you have to take other measures to prevent degradation of your active compounds of interest. You don't need to mill them because they are already so smart. So there we will look into other pretreatments, for example, pulsed electric fields that could make small pores in the cell cultures, and that would help in release the active compounds from the cells without having to apply solvents or having to apply physical stress and causing degradation. So for every type of biomass, we will try to find the most optimal pretreatment resulting in a better extraction yield and hopefully a very active and stable extract in the end.
So this pulsed field idea, so here the cells normally would have a membrane. Which is not impermeable, but generally things don't diffuse across it. Yeah. You apply this electric field and suddenly you have pores appearing, but they close up quite quickly.
Depending on the intensity of the energy, you can have reversible or irreversible pores. So if you put a lot of energy, for example, it's used to treat fruit juices with a high intensity, you kill all the microbacteria in it. Yeah. The microbes are killed. And then that's a kind of to prolong the shelf life, I would say. It's kind of a processing step that guarantees the quality from a microbial safety point of view. But in extraction, reversible pores might be sufficient to get the intracellular compounds of interest out of the cell in the medium without having to do any other extraction steps. So that's a very new way of treating cells with energy using pulsed electric fields. You use electricity, it can be supplied by the sun, very sustainable. You can use water as a medium. It's a very short treatment. Microseconds these pulses are given, and it's very fast on the other hand as well. And the technology is scalable because they have designed a fully continuous line where multiple liters can pass through this field where you give the pulses. It's a tubular system. It can be pumped continuously, so you can process a lot of liquid suspension cultures in a very short time. So these are promising developments in the technology that could help the development in our work package 4.
So a little bit of context for our listeners. Plant cell is not just like a bag containing liquid and chemicals in one space. It's got lots of compartments. It's got a nucleus. It's got all sorts of small compartments known as organelles. And when you talk about producing ingredients, they're often made in in a very compartment-specific way, and they're separated from each other. And there's the way it happens in nature. They naturally separate compounds which could interfere with each other. Mm-hmm. How do you avoid, when you talk about milling and grinding, everything getting mashed up and mixed up together and then all the things affecting each other? Is there a way to stop that happening?
There is a way. For example, heat treatments could destroy enzymes or proteins, and proteins can degrade when we apply temperature. So that's one thing. Every protein, every enzyme has an optimal pH also, so they work under optimal conditions, and that's also a very narrow pH range. So if you would, for example, acidify, it's possible that the enzymes that have a negative effect on the quality of the extract and cause the degradation, that if we adapt the pH, the compounds are not broken down, but the enzymes are not active anymore. So playing around with temperature, playing around with pH can help to prevent this negative effects. While milling and grinding, oxidation, as I mentioned, avoiding that a lot of oxygen is in the system just by flushing with nitrogen or another inert gas during the mixing and milling system, that can also prevent. And we have done that before, and to show that, for example, if you mash an apple, it will brown very quickly because there's oxygen in the air and it will turn brown. But if you flush with nitrogen while mixing, it stays bright pale yellow, and you have a completely other composition of your extract.
We're talking about, let's say, 50 or so potential ingredients we want to try and extract, and maybe a similar or even larger number of potential sources when you count plant cells, all the different species, and the different plant tissues, and then the waste side streams, etc. So do you have to kind of like apply a matrix of different conditions and work out totally customized extraction process for each molecule from each source, just to test all these variations where you can destroy the enzymes without destroying the product and all sorts of things like that?
I'm afraid I have to say yes. I'm afraid we will have to focus on the most potential ingredients which are selected based on bioactivity assays, and really target our efforts on upscaling the extraction process for these most interesting compounds. Because, for example, we know if you just compare an apple and a pear, the same enzyme is present there, but it's acting completely different. And those are quite closely related species, but the polyphenol oxidase in an apple is behaving completely different than a polyphenol oxidase in a pear, just because the pH of an apple is more acidic. A pear has a higher pH. So there's so many peculiarities we have to take into account when looking at the biomass with which we start. And then depending on the compound of interest we want to have in the extract, that we have to take into account so many variables that most often you have to adapt the process really case by case.
Yeah, that sounds a lot of extra work, because it'd be so much simpler if you could find a process that worked in one species and apply it to another.
I'm afraid that will not be the case. So we will have to make some selections with the help of the colleagues in BP5.
Well, this explains why the project is 4 years long and not 4 months long. Talking about the products, and I wanted to ask you, this is probably more of a personal question. So obviously you're very interested in plants and the process of metabolism in plants to make these molecules and extracting them. But the InnCoCells project is specifically about cosmetics. So I wanted to ask you, was your interest, let's say you were interested in the activity of molecules in a cosmetic context, and that led you to studying plants, or were you always interested in plants? It just so happens the InnCoCells project was about that, but the focus was on cosmetics, but it fitted with what you were doing in terms of technology.
I think the second explanation or reasoning you expressed is the one which is valid for me. We have some nice technology within our food pilot hall, which is basically used today for food processing. But for example, the low oxygen milling and fractionation can also be applied for other applications. And in this case, if we start from whole plants where we are interested in bioactives who are very sensitive to oxidation, this low oxygen milling and fractionation can be of value. And I think this is what innovation is about. It's about applying technologies from another field in a new sector, and that can lead to radical innovations which would not exist if we stick applying the same technology to the same applications. So here we have a combination of experts in different fields. My background is currently more in food bioprocessing, but I think there's some valid insights and technologies coming from that field that could help the cosmetic sector as well. And one other example is the fact that the sourcing of the raw material could be different. Yesterday we had a discussion about in VP1 to VP3, we are specifically producing biomass for extraction. But as you mentioned in the introduction, there are potentially other sources that could be relevant for the cosmetic sector. We have byproducts from the agri-food sector, and a point of discussion could be the quality. and the variability in that biomass. But if you look at certain production standards, they are so high in food processing that with certainty we can find relevant sources which are of good quality, where traceability is okay, where safety is okay, that could also be used for other industries. And I think this could be an outcome of InnCoCells as well, to show to these other sectors, look, don't stick to your own business, but work together. And the byproducts you are currently feeding to cattle or turning into bioenergy, they can be used for higher added value applications. And that's also one specific goal of WP4, to look into these byproducts from our own project, but also to use the byproducts from other sectors as a starting point, as a feedstock for extraction. So combining these two strategies, I think InnCoCells can inspire a lot of companies that could work together in the future and not only produce perhaps cosmetic ingredients, but also other relevant ingredients for the bioeconomy.
So on that subject, do you think that the InnCoCells project will have an impact on your research in other areas as well, and on your department in ILVO?
Yeah, I think so, because, for example, in a discussion yesterday, the quality of the feedstocks was expressed, and that the quality control in pharmaceuticals and cosmetics is of a much higher standard than is in agri-food today. I'm not totally sure about that. I think the quality in agri-food also went up regarding the handbooks they have to follow regarding safety, etc. So the biomass they produce, if they look at it as a valuable source and not as a byproduct or a waste fraction, it can be a perfect feedstock for other sectors. And this will lead to new collaborations. And that's what bioeconomy is all about, to work together in a more sustainable way and make better use of this high quality biomass which is produced in agri-food for a much broader range of products, because a lot of cosmetic ingredients are still fossil based in a way. They are chemically synthesized, and by looking at the valuable sources we have in agri-food, I think we can do nice things for cosmetic sector, for example.
A bit of context for our listeners. This is one of the great advantages of the Horizon system, because we have all these organisations collaborating, and today we're collaborating on using plants to make cosmetics, but the technologies we develop tomorrow can be used for another set of collaborating organisations to do something else. And many of the organisations in the InnCoCells project have worked with each other before, or with other partners before, on different projects. Mm-hmm. And it's like building a knowledge bank, if you like, of technologies and processes, etc., which are extremely good news for the future in all sorts of industrial sectors for the benefits of society and to increase the sustainability of all our products and processes. Final question, Bart. If you could have one wish for a positive outcome from the InnCoCells project, what would you like to see it achieve?
Yeah, it would be great if for each of the different platforms that were started at the beginning of the project, that each of these could lead to a functional and very interesting extract or active ingredient for the cosmetic sector, because having a diversity of platforms is always good. I'm already, after 2 years of the project, I'm convinced that cell cultures could have an advantage for a specific application. It might be too costful to use cell cultures, but that field cultivation in another case could be more competitive for another application. So the wish, the dream would be that from each of these different production platforms, we can have an ingredient which passed the TA and the LCA analysis in WP6, for which we proved functionality in WP5, and that the partners in the project and the stakeholders in the group, they are really eager to use these in future products. So that would be a perfect outcome.
Fantastic. Well, we can look forward to that. Bart, thank you ever so much for coming on the podcast. It's been really great speaking to you. I want to say good luck tomorrow with your presentation. Mm-hmm. Thanks ever so much. And for our listeners, we're signing off now from Luxembourg. Great to have you with us again, and we'll see you on the next edition of the podcast from the InnCoCells project. Thank you very much, and goodbye.